thanks very much. Does that work? Yeah. Thanks very much, Norm, for the invitation to come over here and talk about this, and the invitation to be part of this group to look at this somewhat different topic area to the more quantitative talks that we've had in the last couple of days. So basically, I'm going to talk about a topic that's had quite a lot of work in the last 20 years in the research domain, funded by groups such as SCEARC and New Zealand government and NEHRP and that sort of thing. So thanks to Norm and Steve and Nora and Tom and a colleague in New Zealand for some of the assistance to do with this bit of work. So it's a topic area, as I say. It's had a reasonable amount of focus in the research domain, not so much in the practical applications in terms of actually constraining real seismic hazard models, but it's had to have had this research time to sort out some of the issues and the uncertainties. And so what I'm showing here are examples of fragile geologic features. The main class of fragile geologic feature that has been the topic of a lot of the research are these precariously balanced rocks. And this is a fairly extreme example from North Queensland where not many earthquakes occur. And examples of reasonably precarious features from California. This is an example in granitic rocks on the hanging wall of the White Wolf Fault in Southern California. This is an example from New Zealand in schist terrain near a dam site that I've been leading a seismic hazard assessment on for a number of years, and we're now at the stage of using these features to see what they can tell us about hazard in the area. And this is a sea stack feature that was basically right over the epicentre of the Christchurch earthquake in February 2011, and rock motions of over a G resulted in the feature being somewhat shattered. So fragile landforms, they sit around for a very long period of time, get shaken down by strong earthquake shaking. And so if you know the approximate fragility of these features and how long they've been sitting like that, they might be able to tell you something about non-exceedance of motions or what motions they could handle without being shaken down. And then I use the generic term fragile geologic feature because it's not just precarious rocks. You actually have features like this, unstable cliff faces where you have open joints, and if you shook a cliff face like this, you would get a lot of damage. So if you can work out how old the surfaces of the cliff face are and what it would take to bring them down, you can provide some constraints on hazard. And this is an example that I've worked on some years back in Yucca Mountain. And I have to acknowledge Jim Broon. He's the man who first came up with the idea of these fragile geologic features being able to tell us something about seismic hazard, but independent of data sets that are used in seismic hazard models. So I've more or less said the first thing here in my outline, but I've been given these three questions here to address in this talk by Carola and Norm. Diablo Canyon Power Plant, what fragile geologic features are present in the area that could be used for constraining or at least comparing to hazard estimates, and how fragile are they, and some initial estimates of fragility. And I have to say that I've really just started on this work at the power plant, and so the efforts in this area are very preliminary back of the envelope right now. But I have looked at what can be done more substantially there. So a little timeline here. Went into the field with Steve Thompson and Nora Lewowski. Is that correct?
Oh, Lewandowski.
Lewandowski, thank you, and Tom Hanks, to have a look at features that had originally been observed in 2010 by Steve and others, to give basically a second-hand opinion on whether these features were worthwhile for follow-up work, considering work that I'd been doing and applying them in New Zealand and elsewhere. And so, in short, only really saw one of these features as being suitable for follow-up work, but found 3 additional ones that hadn't really been identified before in the same area. So 4 features at least looking worthwhile to study, and all of them at the Double Rock East site, so I'll show you where that is. So the power plant's the star here, and the 3 sites that we looked at, Double Rock East to the southeast of the plant, the intake, in the area of the intake, there's a intake bay, there's a fragile arch, and then there was the crowbar site. So this is the Double Rock site. What we're looking at here are sea stacks that are fossilised. They're basically uplifted sea stacks that used to be eroded and shaped by the sea, but with long-term earthquake uplifts, etc., they're now quite a bit above sea level and not being attacked by the sea anymore. So for assessing the age of these features, it means that there's no interference with being in the modern sea environment. That's very difficult for dating. And so these features are very resistant rock types, Franciscan cherts, and the bedding is pretty much vertical, which gives them these very solid, slabby appearance. They're not fragile in themselves, they're very strong features, but it's more the features that sit on the side of them where the bedding planes are peeling apart just with the aging process and exposure. And this is the Double Rock East site, and that's on Double Rock East, and this is Double Rock West. And this is the feature in profile. So a piece of chert that's slabbing, the bedding plane is opening up, and the feature is sitting there unstably. This is the one feature identified in 2010, but then on Double Rock West, as we walked along here we are for scale. 3 more features. They might be a little bit unclear in this scale and colour, but similar sorts of things to this sort of slabbing feature. So this feature sits unstably on a sloping pedestal. So, and I might also add that the surface here is the surfaces are between 80 and 120,000 years. So these are features with some considerable antiquity to them, and by inference these features would hopefully be in the sort of ages of being thousands to low tens of thousands of years. That's completely unknown at present. So this is a close-up of Double Rock East, and the scale's rather hidden in here, but my height would probably be up to about here. So using the initial easy field-based, very rough assessment of quasi-static toppling accelerations from the geometry of the rock and the centre of mass and the rocking points, if you assume this is a feature that if you shook it, it would fail by toppling acceleration, by toppling, basically coming out like this on its pedestals. So this is something that Jim Broon uses in the field. You roughly guesstimate the centre of mass the vertical and the rocking points. And really for a rock like this, sitting so close to the country rock, it can only really fall in one direction. And so this angle alpha here is the relevant angle for its stability. And so using Jim's very simplistic estimate of quasi-static toppling acceleration, tan alpha about half a g. So in Jim's old scheme of things, that would be not precarious but semi-precarious. So shaken down by reasonably strong shaking, not low levels of shaking like, for example, the Australian feature I showed. And if you instead assume that this would fail by sliding, you get a very similar answer with a very rough Newmark type analysis using slope angle and angle of internal friction, etc. So this is a very ballpark type rough estimate. As I say, this is a very low resolution, less quantitative sort of a topic than what's been talked about the last couple of days. So in the reconnaissance, we also looked at revisited the crowbar site and the intake bay arch, delicate arch site. Now the sea stacks at crowbar, they're more subdued. They're not those very, very steep, hard Franciscan sea stack outcrops. And that's because the materials are tertiary welded tufts. They're hard rocks, but not as hard as Franciscan materials, so they erode away and produce talus slopes. And this was the feature called crowbar, a big boulder sitting on top of this hill. In actual fact, we all thought it wasn't particularly fragile. Take reasonable shaking to bring it down is the impression that we got. And similarly, other features on the neighbouring sea stack. And the delicate arch, while quite a fragile feature, where it is located in the intake bay, makes it access quite difficult. And for dating purposes, it's problematic because it's still at the waterfront. So looking very simply here at the hazard curves for Diablo Canyon, I've looked at the shoreline report hazard curves and tried to get some idea of the sorts of ages, if we knew the ages of these rocks, what sort of age would be useful for the purposes of the hazard. And I draw on work done by Anderson and Brune and Norm, where you basically use a points and hazard space approach, which is a reasonably simple, intuitive process of plotting 1 over the age of the rocks and their toppling accelerations on hazard curves. And so we can't do that at the moment because we don't have the ages of these features. But if we looked at some ballpark fragility values, so toppling accelerations, say if the 0.5 g back of the envelope toppling acceleration, if we looked at where that would plot on this, basically the return time of that is about 1,000 years. But if it was less fragile, say 1 g, the equivalent return time is about 20,000 years. Now that varies depending on the hazard curves you look at. But in essence, what these rocks really, what we really have to find is that if they plot anywhere inside this area of the hazard curve, then there's a discrepancy with the hazard in that the hazard curve is producing ground motions that are occurring stronger than the rocks can withstand too often. And so there's a violation there. They really have to plot somewhere outside of this curve here to be compatible with the hazard curve. So as I say, we don't know whereabouts to plot these values at the moment, but assuming 0.5 g would be their toppling accelerations, then they're only going to be useful if their age is 1,000 years or more. And if we looked at an alternative hazard curve here, this is just going online on the national maps hazard curve, which I did before I got the shoreline report. Half a g rock motions, return time of 1 to 2,000 years, and 1 g 10 to 20,000 years-ish. So basically we need to know more about the fragility and the age of these features, but at least as far as the purposes of this, this workshop, we've been able to identify these, at least identify features that look suitable for studies. So moving forward, what really needs to happen, I've talked about this with people, and basically there's a fairly simplistic type of analysis or series of analysis that we can do, 2D analyses of the stability of these features, focusing on Double Rock East. That's the initially identified feature, and it actually already has been sampled for cosmogenic dating by Dylan Rood some years earlier. He's got the samples sitting there, and he would say his one recommendation is to do some dating on those features, all ready to go. And he's had experience with doing this at Yucca Mountain on similar features. So what I would like to recommend is a simple 2D analysis of the Double Rock East feature, and basically by a variety of methods to work out what it takes to achieve a factor of safety of less than 1, whether from earthquake shaking, and in other words, failure of the features, and that can define the limiting ground motions. And so with a colleague Fernando in GNS, we have this rock slide software, and we can look at 3 failure modes: block sliding as it is in its present geometry, block sliding after disintegration of base due to weathering, etc., or a toppling failure, using the more classical Brune type of analysis. But basically you can do the 3 of these in the software. And as I say, revisit Dylan's samples that he has over in Glasgow and get the fragility age for Double Rock. He does a series of samples and he models them, and the output of it is the age the rock has been in its present fragile state by sampling on the rock and sampling the country rock in behind. And then compare those initial results to the PSH model and see what comes out of that. And then if we wanted to do this really properly, it would involve 3D modelling of all 4 of these rocks, because really, I have to say, there's an emphasis probably in the science domain, and due to funding restrictions, etc., there's probably been too much of an emphasis on the rarities, the occasional precariously balanced rocks that you see around the place, and maybe going too far with over-interpreting them in terms of comparing to seismic hazard maps, cybershake, etc., etc. The key thing that I'm pushing in this is that there is a more substantial defensible result to be had by looking at more than just one feature. And that's why I say the first stage, looking at Double Rock East, is just an indication, but I was very pleased to see more than one feature there. I mean, we're still only talking 4 features, and there's still a lot of uncertainty there. But at least getting through this process, there'd be quite a substantial answer. So looking at all the 4 of the fragile features, possibly we could make inferences about on their ages with uncertainties after having done the analysis on Double Rock East. But use Hosgary Fault or any sorts of relevant time histories with these 3D models to obtain fragilities according to real earthquakes. And yeah, this is, as I say, could potentially be an optional item. And then compare more substantially to the PSH model. So, as I say, it's really preliminary at this stage, and I've only just started on it. But so the conclusions are quite preliminary and forward-looking. So we've identified 4 features at the Double Rock site and the Crowbar site not really being suitable for follow-up studies, and recommended 2D fragility analysis followed by 3D fragility analysis. So I think that's
so the key is if that date comes out over 1,000 years, then there's a chance we could get a constraint on the hazard. If it comes out hundreds of years, then
it's not.
Right.
Yeah, because I think it's at least 0.5 G is the fragility. Probably not 1 G is my sense. Just and age-wise, I would say based on Yucca Mountain work, I wouldn't be surprised if it was in the 10 to 20,000 years of age. It's a wetter environment, so it may be younger than that, but similar features at Yucca Mountain, I was in the 20 to 50,000 years age, and that's in a pretty one of the areas I looked at was a pretty tectonically active environment.
So any questions for Mark? You need to use the microphone.
Your software that you mentioned, is it finite element software?
So,
The software that you mentioned,
yeah.
Is it a finite element software package? You mentioned a software.
Yes. I just didn't get.
Is it a finite element software? Okay.
Yeah.
Hans?
When you're comparing these fragile features and their age and presumably failure accelerations to the hazard curve, are you using the mean curves or a fractale?
No, those were just straight hazard curves.
Those were means. Those were means.
They were means. Right. Okay. The national maps, it was I think the full sigma was in there.
Yeah, but it's a mean hazard. You can use he's asking if it's mean or the fractals there. If the dates are long enough, you can use them to try to eliminate or rule out some of your fractals.
I have a question. Hi. Does this take into account the direction of shaking? Because it looked like for some of those, whether the component is north-south or east-west, does it take all of that into account as well?
Yeah, those features really will only it'll only be relevant in terms of shaking that is normal to the Hosgary Fault.
Correct.
I mean, it's only going to shake, only going to topple in one direction, so it will only be relevant to shaking that's more or less normal to the Hosgary Fault.
Okay. That's what I was wondering. So, like, for instance, you're getting some path effect from a different direction. It might necessarily topple it, but... Yeah, well,
if you did the 3D analysis, you'd have the 3D geometry of the rock, and then you could throw you could throw time histories at it from any direction. It would be less fragile in that, in shaking that's parallel to the bedding.
Okay.
Yeah.
Okay.
So you could actually still probably use them, but for higher levels of fragility.
Okay.
Yeah.
Understood.
Yeah. The ideal thing is to have one of those beautiful features like the North Queensland one where they're fragile in all directions.
Right, okay.
Yeah.
So it might be like one particular ground motion in one direction, but something in a different one.
Yeah.
Okay.
Yes, that's right. And the thing is to find features on various orientations. But yeah, we're dealing with bedded chert where all the landforms are lined up in one direction. So it's a bit limiting. It's not like some of those sites out in the Mojave Desert. Yeah, but you know, it's what we've got.
Yeah. One last question, Bob. You had one last question.
I've heard Jim Brune give talks about this a dozen times or even 25, and he always starts with the same warning, which I know you know, but I want to make sure everybody else understands. Imagine you have 3 features out there that you saw, but I want you to imagine that 10,000 years ago there were 300 of them, and only 3 survived. So 297 of them toppled, which really means these represent the 1% point on a fragility curve. The few survivors. If that's true, then your estimate of the motion it takes to topple them in whatever space you need could be off by very large factors, like 2 anyway, or maybe even more. And you have to know something about this question before you can proceed very far within factors of 2. And factors of 2 that's 2 in whatever you call the size of the motion. That's a big factor.
But there would be,
of course,
if there was hundreds of them, we should see their bodies laying on the ground.
Well, you don't know. Maybe not.
This is a question that I've raised in SCEC research and had, well, you know, minor SCEC funding, but still get SCEC funding to look at. And we've been, Dylan Rood and I have been undertaking a review of all the well-studied precarious rock sites, and we actually see a much larger, well, you see the rare precarious features, but you see them in terrain where you would expect, if they were really telling you something about the ground motion, the suitable geology there is such that you should see hundreds, if not thousands of them.
I mean, I agree. I was exaggerating to think it was 1 in 100, but still, once you've thought about it that way, you do have to try to think about the ensemble of which there's a denominator, of which this is the numerator.
Yeah. So, I mean, there's a site, Lovejoy Buttes. It's 15 kilometres from the San Andreas Fault. There's 2 precarious rocks that a really big thing have been made of. But there are hundreds of semi-precarious ones which give you fragilities of about 0.5, 0.6, 0.7 G, and to me that's probably quite consistent with San Andreas earthquakes, and it's had many tens of San Andreas earthquakes pass there, so it's something I'm pushing at the moment. I argue a lot with Jim about this statistical remnants thing. Diablo, I still have to have more of a look around there, but to see if we can possibly identify more than just 4, to see whether we've got a stronger signal there. But yeah, on the same page.
All right, we need to wrap up, so thanks, Mark.